Welcome to Chemistry 111, of course, on this Monday, the 21st. We are going to pick up where we left off on Chapter 6, learning about Lewis structures and how do we treat them. We had last talked about the basics, the rules of Lewis structures, which were step 1, determine the number of electrons. Step 2, determine the central atom. Step 3, single bonds to every atom. Step 4, put lone pairs on the outer atoms. Step 5, if there's any electrons left, put them on the center atom. Step 6, rearrange electrons into double bonds to give an octet to the center atom. And step 7, which was double check and make sure everything is correct. We then went on to talk about organic compounds, how we do that. And while they have more than one center atom, we can use the chemical formula as a hint of what type of fragments we need to break these into, such as ethane, which would be CH3CH3, two CH3 molecules single bonded together. Okay, continuing right on from there. All those were considering just neutral compounds. So how will we deal with ions? These polyatomic ions. Well, ions are not by necessity any more difficult than what we have, because what does an ion essentially entail? It entails either an absence of electrons or an excess of electrons. So when we do a Lewis structure for a charged species, all we have to do is to account for any changes in electrons. If we were to do a charged species like NH4 plus 1, ammonium, you would think, okay, nitrogen typically has 5. Each hydrogen typically has 1. So you would have 9 electrons to deal with. But because it's NH4 plus 1, 9 electrons goes to 8. And so we would create a structure that is 1 less. If we were doing something like, trying to do some hydroxide, which is OH 1 minus. Oxygen typically has 6. Hydrogen typically has 1. You would think of OH as having 7 electrons. But because it's 1 minus, it now has 8 electrons. And so we would draw the structure with 8 electrons instead of 7. And when you finish the structure, typically we're going to put this structure in brackets with the charge as a superscript out front, because we don't necessarily know, we're not saying which of these electrons is the extra. We're just saying the structure is charged. So looking at that real quick, those two examples. NH4, which is plus 1, as I said, 8 electrons. N, H, H, H. There's 4 H's, 2, 4, 6, 8. I've already used up all my available electrons. So ammonium would just be N with 4 H's off of it. And instead of having 9 electrons we have to deal with, we have 8. In fact, this makes sense from what we know of the octet rule. Because nitrogen, if we did ammonia, NH3 would have had an octet and would not want to make another bond. Having 9 electrons to deal with would give us a stickler of a problem where all hydrogens have a doublet, Nitrogen has an octet. Who wants to get that 9th electron? No one does. No one does, so it doesn't make sense to need that 9th electron. Same thing with hydroxide, OH minus. That would typically be 7, but now it's 8. OH, so that's 2 electrons. We have 6 left to put. Hydrogen doesn't need any, so we put 1, 2, 3, 4, 5, 6. There's the remaining 6 electrons. So OH minus is just that structure. How would that differ from, say, water? Water, H2O, would also have that octet, except instead of that lone pair right there, it would have a single bond to hydrogen. In both cases, the O has an octet. But in this case, without that extra hydrogen, it needs another electron to make that stable. And so that is how we are going to deal with these guys. This is how we're going to deal with these charged species. We're going to have to take into account the extra electron or lack thereof. And just add that into step 1. Add that into step 1. Now there is something we briefly talked about before, but we also need to consider, and that is resonance. And sometimes there's more than one bonding arrangement will be possible. They may only differ from the placement of a multiple bond or the placement of a lone pair. But the difference in this bond placement is going to be resonance, and this is going to be the examples you see at the top are examples of resonance structures. In our mindset, you could maybe imagine me rotating this structure 180 degrees. Doesn't matter which 180 degrees? Not really. I mean, as long as you don't rotate it on this axis, as long as you rotate it, flip that oxygen over there, or rotate this, and you can rotate this over there in 2 dimensions. You would get the same structure. But one thing you have to realize is there is no actual rotation going on. This is a literal, the bond swings over. The lone pair comes down, makes a bond. This lone pair swings over here. And so these are 2 distinct structures. If I had a way, and there is a way to label these oxygens, to instead of being O16, you had O18, like a heavy oxygen. You could distinctly tell the difference between this structure on the left and this structure on the right. And so these are 2 distinct structures. Now, what happens in real life is we get what's called a resonance hybrid, which is somewhat combination of the 2. Now, we have a mixture of a double bond and a single bond. And so what we actually see when we look at the structure in real life under normal human speeds, we see bonds that are somewhat between a single and a double bond. Not quite as long as a single bond, but not quite as short as a double bond. Not quite as strong as a double bond, but not quite as weak as a single bond. So we get a mixture of the 2. And in fact, this stabilizes both of these structures. If I was just the left structure or the right structure, it would be relatively easy to remove that single oxygen. But because I have the possibility of this mixture, both ones are stabilized. And in fact, there's a lot of things that happen through this stabilization effect. These electrons become what's called delocalized. We get a delocalized bond. Breaking down what that means. It means instead of being located at just one spot, we're allowed to kind of rotate around through this cloud. These electron clouds, we're able to move around so these electrons aren't stuck in one place. Now, please note, the single bonds are localized as they come. The single bonds are stuck there. But this double bond is able to shift from here to here. These lone pairs are able to shift from around the atom into the bond. So they're delocalized while the single bonds are very much so localized. But this is going to create some degree of stability in this structure. And we'll see this going on. Whenever you have more than one structure that differs only from the placement of double bonds and lone pairs, we are going to have this resonance structure. If I find a different way to draw this that is still valid, that no longer becomes a resonance structure. You might be able to draw an idea of this guy with a O, like some sort of ring. That would not be considered a resonance structure with our current setup. Some sort of three-membered ring. That would not be resonance because it differs in that we have another single bond. Normally, these oxygens would not be connected. So that is a different structure altogether. So resonance is only when we are shifting around our double and triple bonds and our lone pairs. One other thing we will learn to deal with, and this is going to have a lot to do with different properties of these guys as we move forward, is electronegativity. So electronegativity will fit in really firmly with our two trends about electrons. We learned last chapter about ionization energy, the ability to, how easy is it to lose an electron? And the electron affinity, which is how much energy is gained when you gain a new electron. When we think of those two in conjunction with each other, we get electronegativity, which is the ability of a bonded atom to attract a shared electron. Typically, typically, covalent atoms, we think of that sharing electrons. And sometimes, and usually, we want to think of them as an equal sharing pair. But in reality, depending on where this atom is in the table in comparison to the other atom bonded to it, we can have an unequal sharing situation. I mean, obviously, if I tried to bond a metal with a non-metal, there is no sharing involved. And in fact, we have entire extraction of an electron to make the charge structure that is our cation-anion pair. But if there is somewhat covalent bond, we can still have an unequal sharing, so much so that it is like an ionic bond, but the electron is still shared. So essentially, when the nuclei of both atoms have different strengths. When they're sharing the electrons, one atom is pulling the electrons more so to its side of the bond. And so we see a larger negative charge on one side. So the greater the difference between these two numbers you see on this chart, the greater the electronegativity. You can see the metals down there, very low, very low. You can see the nonmetals typically high, and it spikes up at fluorine. Fluorine has the highest electronegativity. Remember, Fluorine had the lowest, had the highest ionization energy, meaning it was least likely to lose an electron. Fluorine had the highest electron affinity, most likely to gain an electron. So, of course, fluorine is going to have the highest electronegativity, the ability to attract electron. So, if I put fluorine coupled with itself, you have two fluorines together. They have the same electronegativity. There's going to be a perfect sharing of electrons. Neither is stronger than the other. It's like a tug of war. But if I put fluorine with a hydrogen, we're comparing a 4 to what, like a 2.1, something like that. I can't really read it too well. You're going to have like a 1.9 unit difference. And so the fluorine will be attracting a lot of that hydrogen's electron away from the atom. We can compare the nitrogen to, say, a hydrogen, or nitrogen to a carbon, or nitrogen to any of these guys. The guy who is larger in electronegativity is considered the more negative atom, the more anionic. What we're going to see in our Lewis structures is the central atom is typically the atom with the lower electronegativity. It just so happens that guy typically comes first in the structure name, because we name structures usually cation first. Higher electronegativity tends to have more lone pairs because they're able to stabilize that. We're able to pull electrons away, which is why we typically put the lone pairs on the outer atoms first, the ones that are more electronegative. So we're going to take this into account. Now, here's where we get a little tricky. There is a concept called formal charge. In the case of multiple resonance structures, some of them may not be equally stable. Some of these might not be the best resonance structure. And how can we determine which one is best? And that's where formal charges come in. Formal charges is a form of electrical bookkeeping. It's essentially what we're going to do when we look at the structure at the very end. We're going to count how many electrons seem to be coming from the atoms, and how many electrons should they typically have. Carbon, for example, has 4 valence electrons. If carbon is making 4 bonds, it has all 4 of its valence electrons. It would have a net charge of 0. However, if carbon with its 4 valence electrons were to make 3 bonds and have a lone pair of 2 electrons, even if it has an octet, it would be considered to have a formal charge of 1 minus, because it has 1 less electron than we would typically expect. 1 more electron than we'd typically expect. If, on the other hand, well, let's look at our ammonium example up top. Ammonium, we're looking at nitrogen in the center with an octet. Nitrogen typically has 5 electrons. It is making 4 bonds. It is showing that it has 4 electrons around it. In this case, nitrogen has 1 electron less than we would typically expect for nitrogen. And so it would have a formal charge of positive 1. So when we determine formal charges, we're going to count half of all shared electrons as being with the atom, and count all of the lone pairs as being with the atom, and compare how they match with the valence electrons. Now, when we add up all formal charges, the formal charges should add up to the overall charge. If we have more charges than we have overall charge, something screwed up. So double check your structure. But typically, the most stable structure will have the smallest formal charge or no formal charge at all. If we have to have a formal charge, we will want to put the negative charges on the atom with the highest electronegativity and the positive charges on the atoms with the lowest electronegativity, if that is possible. Please note, there are some funky structures that I will show you. That is not always possible. We can't do that and still achieve an octet. We can't do that and still achieve an octet. So we're going to stick with this is a secondary effect to the octet. If we can get more than one structure that everything has an octet, choose the better one. Typically on a test, I'll say choose the best possible structure instead of just a valid structure. But we'll take that when we go there. First things first, we're going to draw some structures here and try to put formal charges on them. We have nitrate, thiocyanate, and I'm trying to think, triazonium. I'm trying to remember how we call that thing, but N3 1-. All these have charges. So, step one. Step one is still true. Count the number of electrons we have. We have to consider the charge, but so N, 3, 1-. N has 5. There is 6 from each oxygen. 6 times 3 is 18. And we have 1 from the charge. So what we have 24 electrons. That is the same. We must then go, what is the central atom? We learned that the central atom is typically the first in the formula, which is N. But now that we have electronegativity, we can also think of this in terms of which guy is least electronegative, also N. Electronegativity is highest on the top right, lowest on the bottom left. Since nitrogen is to the left of oxygen, it is less electronegative. So put N, O, O, O. See if this. Step 3, bonds. 3, 2, 4, 6. We're down to 18. Now we're going to put 1, 2, 3, 4, 5, 6. That has an octet. 1, 2, 3, 4, 5, 6. That has an octet. 2, 3, 4, 5, 6. That has an octet. I've used up all of my electrons. Nitrogen has 0 electrons. Nitrogen has 6 electrons. It needs 2 electrons. There's 0 more electrons I can place on that. So what can I do? Step 6, shift electrons. I could shift a lone pair from oxygen on the left. I could shift electrons from a lone pair and oxygen on the right. I can shift electrons from a lone pair and oxygen on the bottom. All of these will result in an octet. And if that was all we needed to do, put a negative there, that is a valid Lewis structure. But let's check our formal charges right now. Oxygen should have 6 electrons. 1, 2, 3, 4, 5, 6. Formal charge of the bottom oxygen is 0. This guy, 1, 2, 3, 4, 5, 6, 7. Formal charge of -1. 1, 2, 3, 4, 5, 6, 7. Formal charge of -1. 1, 2, 3, 4. Nitrogen should have 5. Formal charge of +1. Looking at the structure, we have negative and a positive cancel, and we have another negative. The net formal charge is 1-. It matches with the actual charge, 1-. That is okay. The formal charges are on the negatives are on the most negative atom. The positive is on the least negative atom. That's still good. Could we draw a different structure and still be correct? Yes, because of resonance. We could instead imagine, as I said, N double bond O, single bond O, single bond O. Or we could move the double bond over to the right. These are two of the 3 possible resonance structures for this compound. So that would be nitrate. Thiocyanate, S, C, N, 1-. We've done this one before, but now we have a little bit more to think about. Sulfur is 6. Carbon is 4. Nitrogen is 5. +1. We have 16 electrons. 16 electrons. S, C, N. That's used 4. That's down to 12. Going to put 6 on nitrogen, 6 on sulfur, and that uses all of them up. Octet, octet, quartet. So we are going to shift electrons to make an octet. So I have to shift 2 lone pairs. I could shift 2 from nitrogen, I can shift 2 from sulfur, or I could shift 1 from each. So I'm going to do all 3 resonance structures, and we'll look which one is the better one. I'm going to start with 1 from each. And then okay, so this is our 3 structures. So let's look at the top one first. Formal charge-wise, sulfur should have 6. It has 1, 2, 3, 4, 5, 6. As a net formal charge of 0. Carbon should have 4. It has 1, 2, 3, 4. It has a net formal charge of 0. Nitrogen should have 5. 1, 2, 3, 4, 5, 6. We put the formal charge on nitrogen. Looking at this structure, carbon 1, 2, 3, 4, formal charge of 0. Nitrogen with 5, 1, 2, 3, 4, 5, net charge of 0. Sulfur has 6, so it should have 1, 2, 3, 4, 5, 6, 7. This structure were triple bond between C and the N. single bond between C and the S puts the formal charge on sulfur. Then finally, triple bond between sulfur and carbon. Sulfur should have 6. Sulfur should have 6. We have 1, 2, 3, 4, 5. Plus 1. And carbon still has 0. Now nitrogen should have 5. Has 1, 2, 3, 4, 5, 6, 7. It's a formal charge of 2 minus. Positive 1, negative 2 still adds up to a negative 1 overall charge. So based on the rules of formal charge, this structure is the worst. It is a valid Lewis structure. It is a resonance structure that still exists, but it is the least stable Lewis structure because it has the most number of formal charges. The 2 above structures only have 1 formal charge. This structure has 1, 2, 3 formal charges. And so this one would be the least stable of all the ones. Now looking and comparing structure 1 and structure 2, we have to look where these elements are on the periodic table and what is the relative electronegativities of the two. Look, going back 1. We see right here, nitrogen versus sulfur. Nitrogen versus sulfur. Nitrogen has a greater electronegativity than sulfur. And so if we wanted to compare these two structures, we would want to put the formal charge on nitrogen rather than on sulfur. And in this particular instance, the top structure would be the most stable. Does that say this structure, this middle structure, does not exist? Absolutely not. There is lots of metal chemistry where you see bonding of thiocyanate either through the nitrogen or through the sulfur, depending on the situation. So these two resonance structures are still very much so valid. It just so happens that this one is more abundant more often at the time. But this one would be the best one, but that does not invalidate that one as a possible structure. And finally, N3. N3. It's just like O3. Just like O3. There is 3 nitrogens bound together. Not in a ring, but in a straight line. N3. So dealing with N3 1 minus. N3 1 minus. So 3 times 5 times 3 is 15 plus 1, 16 electrons to deal with. N. Doesn't matter which one's centered. No, they're all N. That uses 4 electrons. We're down to 12. Generalized rule, put all the electrons around the outer core. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Just like thiocyanide, we have to now make some double bonds. And just like thiocyanide, we're going to have those options. Well, we won't have as many options because of symmetry. But we can have the N, we can have the 2 double bonds, or we can have the triple bond option. So let's look at the difference between these two options. My marker. And okay. Nitrogen, in all cases, should have 5. In this case, 1, 2, 3, 4, 5, 6. Formal charge of 1 minus. Formal charge of 1 minus. 1, 2, 3, 4. Formal charge of plus 1. Negative 1, positive 1, negative 1. Add up to negative 1. N3, 1 minus, negative 1. That's our situation. Looking at here. 1, 2, 3, 4, 5. Formal charge of 0. 1, 2, 3, 4. Formal charge of plus 1. 1, 2, 3, 4, 5, 6, 7. Formal charge of 2 minus. So these two structures, no matter what, we're going to get a positive charge on the center nitrogen. We're kind of caught between, do we put 2 formal charges on each nitrogen or 1 really big formal charge on 1 nitrogen? And typically we will want to have the smallest formal charges. So the top structure would be a little bit more stable. Do both structures exist? Yes. But we have to kind of play around with which one is more stable based on formal charges. But if I ever ask you just draw a valid Lewis structure, either one of those two will work. Because either one of those two, all atoms will have an octet. Okay. So, the best Lewis structures should have all valence electrons from all atoms, adjusting for the ionic charge. The best Lewis structures should have octets and duets on all atoms whenever possible. I know I'm saying valid here, but it really should be the best. The best Lewis structures should have the smallest formal charges, whose sum total is no greater than the overall charge. And the best Lewis structures should consider all reasonable resonance structures. Obviously, you can't draw all of them all the time, because sometimes we don't really have that option. Now, there's a couple exceptions to the octet rule. Now, not all atoms will necessarily obey the octet rules, but those who don't will fall into either 2 categories. We're going to have some cases of incomplete octets. We've already seen one of those early on when we looked at boron. Boron is going to have a tough time getting a completed octet. But the more unusual one would be called the expanded octet. So molecules with incomplete octets simply won't have enough electrons to give the center atom an octet. The most notable exceptions are groups 1, 2, and 3. Like obviously lithium, beryllium, boron, and aluminum. But we're going to occasionally have situations where nitrogen is going to be stuck with 7 electrons. There's just no way to do this where we make a octet. We'll have an odd number of electrons. So whenever you're counting up electrons for the total number of electrons, hopefully you notice that every time when I added up all the electrons, we had an even number. 16, we had 24, we had 12, we had 8. We had some combination that's going to give us an even number of electrons. If we ever have an odd number of electrons, for whatever reason, we're stuck, unable to make an octet on one of these atoms. In this case, we have what's called a radical, which is an unpaired electron, which is typically very highly reactive. For those who will eventually go on to organic chemistry, there's a whole series of reactions called radical reactions, where you use light to split these atoms apart, and they react very quickly. In fact, a lot of these radical reactions are reactions that go up in our upper atmosphere. The ozone is going to absorb light, creating radicals, which will then recombine and form oxygen as the ozone is consumed. But many of the pollutants we produce have these radicals that will then go up there and recombine and react and form various other pollutants like acid rain, among other things. Now, the expanded electrons, the expanded octet, is a class of compounds that, taking into account our electron orbital theory, these are atoms that have access to an empty d orbital. They have access to an empty d orbital. Remember, we do not want to put electrons into the next principal energy level, which is why we stopped at the octet. We filled up the p and we stopped. Well, atoms of group 3 or lower, so group 4, group 5, group 6, all have access to an unused D. Remember, 3D doesn't show up in the periodic table till row 4. 3D is available at row 3. It just doesn't get used till row 4. But it's still there, like an attic that you just discovered your house had. It's empty. And suddenly, well, I have all this junk that's sitting around. Let's go shove it in the attic. Well, that's what these expanded octets are like. We have all this extra electrons. I don't know what to do with it. Let's go shove it in this unused d orbital attic. And so these guys with the expanded octet can occur anytime the central atom is row 3 or below in the periodic table. So if it's phosphorus, it's silicon, it's sulfur, it's chlorine, selenium, bromine, germanium, arsenic, antimony, tellurium, iodine, any of these guys can have an expanded octet. There's anything below that. You could go tin if you really want to. You could go lead. You guys could all have expanded octets, but then we're getting into some of the metals. But one thing you will not see is any group 2 atoms having an expanded octet. So carbon, it's straight out. Nitrogen, wrong. Oxygen, impossible. Fluorine, not going to happen because they have 2p. There is no 2d. There is no 2d. We stop at 2p and then we go on to row 3. So all the guys we have been dealing with so far had carbon had a row 2 element as the center atom. So we haven't had to deal with this. But this is where a lot of the oxyanions get their 4 oxygen bonds. When we get these oxyanions like sulfate, phosphate, perchlorate, perbromate, the reason behind these guys is because of this expanded octet. Fluorine did not have an oxyanion because it did not have a chance for an expanded octet. Chlorine can do an expanded octet, and so chlorine saw an oxyanion. So a lot of the weird things that came around when we named these guys all come back down to this. Now, I will stop after this slide, but starting next class, we will do some examples of these expanded octets. So looking at the Lewis rules, just looking at the rules again, we sum up all the valence electrons, we count for the overall charge. We're still going to select the central atom first in the formula, but it should also have the least electronegativity, and it can make the most bonds. Once again, the formula is the key. Connect all other atoms to the central atom by single bonds. put the electrons on the, oh geez, what the heck? Distribute the electrons to the outer atoms to give an octet or duet whenever needed. Put any remaining electrons on the center atom. All that's straightforward. Move lone pairs to give our multiple bonds, to give our central atom an octet. So what really got changed is 7. Previously, it's checked that all electrons are accounted for, that we have the octet and duet rules. But now it's kind of, look, is the center atom period 2? If it's period 2, does it have an octet or less? In case of boron, beryllium, or nitrogen, sometimes you're going to have less. If it's group 3 or group 4, it can have greater than an octet. And finally, we're going to check that all formal charges are small and assigned to atoms of the appropriate electronegativity. So we want a structure that has the least formal charges. And that's where we're going to stop, because I don't think we fully have enough time to look at these practice problems. With that in mind, I thank you for your time. I will see you again on Wednesday. The test has been sent out. You don't have to do it till Sunday before midnight, but it's been sent out. You have all the information you need to know in order to do it. So take your time. Have a good day.